This week we're ready to finally do something that resembles the quantum field theory you've probably seen in popular science videos or in popular science books. We're going to take a picture like this and interpret this diagram as the amplitude for a particular process in quantum field theory, one that we've been building over the past couple of weeks. Now, if you remember the story so far, before we get to this, I will summarize the story so far, and also we'll spend most of today building up the dictionary between these pictures and certain amplitudes. So the story so far we've built what can legitimately be called a relativistic quantum field theory. Namely the Klein-Gordon field. And then we were perhaps disappointed to realize that this is a free quantum field. So it's relativistic, it gives a unitary representation for the Poincare group, but it's not in any sense going to model the world we find ourselves in because there's no interactions between the excitations of this field. And to remedy that, we added interactions which we argued or hoped, on the basis of hope really, would be Lorentz invariant. So we've added interactions via an interaction term, h int, and of course in the previous lectures I said that there is an infinite number of possible local interactions you could add to such a theory, but for various reasons this turns out to be almost the unique one that you can add. So we'll spend most of our time discussing this particular interaction in the context of the scalar field. And then we realized, well, you know, we went from being able to calculate everything to being able to calculate nothing when we add this term here. And then I discussed how to deal with problems where there's an interaction term. And that particular interaction term has a small coupling constant here. So this thing here is small in quote marks because it's at this precise moment where we leave the land of mathematical rigor and we have to exploit our physical intuition to justify calculations whenever we do them. So we discussed perturbation theory, which applies to systems like this one here, Klein-Gordon plus h int, and tells us, at least to low orders in lambda, what the values of various physical processes should be, the outcomes. And then the last thing we've been talking about in the story so far is the observable quantities that we want to focus on. And the ones that we focus on, while not being directly physically observable, are at least the ones that allow us to calculate directly physically observable quantities. These quantities we focus on are these endpoint correlation functions known as Green functions, or Green's functions, depending on which school of thought, which school of pronunciation and you belong to. These Green's functions are defined to be these time-ordered vacuum expectation values. And that's in the Heisenberg picture, not the interaction picture. Yeah. So these are the quantities that we will focus on, observable quantities with an exclamation mark there, indicating that they're not themselves directly observable, but they are not far from being directly observable. And as I argued previously, there's many possible things you could claim to be observable in a quantum field theory. These at least determine all the results of scattering experiments between distant particles. We're not quite done. In the last lecture, we proved one more statement that allows us to connect perturbation theory, or time-dependent perturbation theory, with these objects here. These objects here are not directly approximable via perturbation theory. Well, not easily, right? There's some calculational steps that goes between objects like this and quantities like this. And we proved a technical lemma in the last lecture. And it's this one that allows us to deploy perturbation theory on the problem of calculating these quantities here. And the result we proved in the previous lecture was that these Green's functions, are precisely given by the following formula. So this is the full interacting vacuum here. And that's not an easy quantity to calculate when you have an interacting theory. But we argued that these quantities are at least, if you could calculate the following objects, then you would be able to calculate these quantities. So this object here are the field operators in the interaction picture. And this S hat, oh yeah, let me just label the data here. We have that this guy is the vacuum for the Klein-Gordon field, which is an easy thing to calculate, well, easy-ish. And this S hat operator is the limit. No. This S hat guy here can be evaluated by taking this following limit here. For all psi and xi. So this is this S operator, S matrix. That's all the pieces of our story so far. And today we put it all together and we make our first steps towards calculating the results of interactions in a relativistic quantum field theory. So to summarize, we've built a relativistic quantum field theory which was free. We added interactions which we argued to not destroy Lorentz invariance because they were local. And certainly their classical analog doesn't destroy Lorentz invariance. We discussed perturbation theory to deal with these added interaction terms. We then focused on some observable quantities that we want to approximate by perturbation theory. We made that task of approximating them easier by relating them more directly with the objects that we want to perturb around. And today we're actually going to do the perturbation theory that we need to do to calculate these objects, at least to order lambda and lambda squared. There's one more ingredient that it will be extremely convenient to discuss before we really start summing up terms in a Taylor series, and that is how to deal with expressions that have powers of h int in them. So if you stand back a moment and just look at this expression here, let's think, what is it that we need to do to calculate that expression there? Well, we're going to need to be able to evaluate, in the very least, expectation values of operators in the interaction picture. That's kind of like the bare minimum of what we need to do to be able to calculate this expression here. I mean, even to 0th order, when lambda is 0, calculating gn x1 through to xn requires us to compute some expectation values of time-ordered products of operators in the interaction picture. It's the bare minimum that we need to deal with. And for that, we're going to need a special tool.
This time ordering operator makes the argument in the correct order in time.
That's right,
And
yeah.
the S is not time dependent, isn't it?
Ah, yeah, okay. Let me then stress the point there. So the question was, the time ordering operator puts all the operators in the correct order in time, and the S operator doesn't apparently depend on time. So how does the time ordering operator act on S? I guess is another way of saying the question. Is that correct? Yeah. So S actually does depend on all these operators for all times. Okay, it's a little bit implicit, but let's write it out. So first of all, let's just look at this operator here. That's the S operator is some kind of limit of this thing here. Now step one is I'm just going to write out h int. Right? We don't need that there. We can just put in what it is, which is phi in the interaction picture. T x dt d3x. So even inside this S operator here, we have the exponential of operators in the interaction picture. But we don't just have any, we don't just have one, we have the integral over all time of these operators here. So if you start expanding this expression, this is before time ordering, see there's no time ordering here. Let's expand out this exponential here. We know how to do that, it's an exponential. So this is really the only Taylor series you ever really need to know. So if I call the exponent big X, then we've got some series in, to the power 4. We've got some series in this exponent here. So let's take a look at the first couple of terms. So the first term is in fact a minus I d4x lambda on 4 factorial phi hat 4I on x. Now we're using relativistic notation. And then we've got plus minus I squared on 2 factorial, the double integral, lambda squared on 4 factorial squared, phi hat I to the 4x y d4x d4y plus dot, 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 right? Lots and lots of terms. They go on forever. Now, what happens when we apply the time ordering operator to all of this? Not that the time ordering operator is an operator, but what happens if we apply the time ordering thingy to this? Well, sort of nothing happens at the beginning, right? The time ordered version of this is just I minus I d4x blah blah blah, right? But at second order we see something happen. At second order, when x naught is bigger than y naught, nothing takes place when the time ordering thingy touches it. But if x naught were less than y naught, then it gets exchanged. So this integral breaks into two integrals, if you like. There's the integral over x naught being bigger than y naught, in which case that's okay, that's already in time order here. And then there's the integral, I'll just write ds. No, I guess it's clear. d4x, d4y. Plus, there's another integral, right, where these guys have to be exchanged around because they're in the wrong time order. And we have a y here instead. And then as the terms increase in order, the time ordering operation does more and more complicated things to its argument. Now that was just on the S operator expanded out to arbitrary order n. You can see now how these things will get intertwined with each other as I do this expansion. So suppose I take S, I replace it with this long, horrible expansion here. I stick it in here. And then you've got, this infinite series on your paper. And then you start multiplying that infinite series by these operators here, which are at some specific times, x1 through to xn, x1 naught through to xn naught. And then you apply this time ordering operation. Well, it intertwines all the operators in the series for S with the operators that are pre-existing here in the argument of this expectation value. So this time ordering operation is horrendously complicated, what it actually does to this combination of S and these phi hats. So that's one way of interpreting that expression. In the proof that we supplied in the previous lecture, another way of doing it is realizing that S is this time-ordered exponential propagator. So between times that are present in this expectation value here, S is just the normal propagator. That's what we did in the previous lecture. But I think given that this is how we're actually going to use this expression, that maybe is a more revealing explanation for why the time ordering operation does something deeply non-trivial to things like this. And I hope it's clear that when you substitute this big series into this expression here, we're going to have to deal with expressions like that, where this n is disconnected to this n. So I'll make this like an m here. So m is at least as big as n. We're going to have to deal with expressions like that. And furthermore, once we've dealt with them, we're going to have to integrate over them because there's all these auxiliary variables that get added in as you add powers from the Taylor series. But let's first steps first, right? Let's deal with an expression like that. How do we compute an expression like that at all? That's mostly today's job. And it turns out that we can do that. We can actually compute this expression very accurately. We'll have a closed form answer for how to calculate this expression within about half an hour, I hope. And the way to deal with it is to start thinking about the 2-point version of this, to warm up. You know, you get started somewhere, and it turns out we actually know how to calculate that. All right, that's our goal today. Calculate this. And we're going to start with some notation, and it's an unfortunate notation, but I have no choice in the matter here. It's just what people use. Let's start with the fact that we actually know an expression for the interaction picture field operator. We actually know what this object is in terms of annihilation and creation operators. We've done this already. Right? Many a lecture ago, we actually calculated that this object in terms of the annihilation and creation operators. Now, there's some things worth pointing out here because it's probable that there's confusion somewhere. When there's an underline, that means a 3-vector. So just to remind you where P, no underline, is omega P, that's a 3-vector. And omega P is square root P squared plus M squared. Yep. Oh yes, thank you. The P squared in the square root has to be underlined, otherwise, yeah, it's no good. Good. And finally, you see no underline here, so P dot x is P naught x naught minus P dot x. So that is an expression we've already calculated. And we're going to give names to this term here and this term here. So it's an unfortunate notation because there's a plus here, and that corresponds to the minus term here. I'll write it out again in a second. And there's a minus here, and that corresponds to like a plus up here, and also a creation operator with a dagger on it. So it's really the wrong way around, the notation. It'll no doubt cause you some confusion. But we're stuck with it because that's what people use. Good-o. We've broken up phi I into two pieces, phi plus and phi minus. Notice I've dropped the I. Okay, I'm going to do that from now on. I'll even write that out explicitly, that warning. Yes, the warning. It's too super annoying to write I's all the time. From the context, it should be clear that I'm always talking about the interaction picture. If occasionally we talk about the Heisenberg picture, then we'll definitely put H down here, or Heisenberg down there or something. And we have no reason to talk about the Schrödinger picture again in this course. So we're more or less safe in this operation of dropping the I subscript. So now let me write out what phi plus and phi minus actually are. So phi plus just to make sure that's absolutely clear. That's phi plus right there. It's just the first half of the expression for phi I. And phi minus is its adjoint. There we go, phi plus, phi minus. And why would we do such a thing? Well. Take a look at that expression there and imagine breaking it up into phi pluses and phi minuses. If that irritating time ordering symbol wasn't there, then we'd be able to calculate that super easy. So the main reason to do this decomposition here is just this following observation, right? That phi plus x, when applied to the Klein-Gordon vacuum, does something real nice. Right? It's got the simplest possible value you can imagine, 0.
Sorry, but please choose a symbol than a plus because it's very similar to the dagger.
It's very similar to a dagger, yes. I'm not going to use another symbol. This is the symbol that's used in all the literature. As I said, I have no choice in the matter here. If you want to be able to read any book on this subject, you need to have to deal with this fact that the phi plus and the phi daggers look very similar. It helps to realize that phi dagger is phi. So if you see me write phi plus and you think it might be a dagger, then you might think, why would you write a phi dagger if it's exactly phi? Yeah, see, that's meant to be more daggery. But it's the notation we are stuck with. I'm afraid we have thousands and thousands of papers in the literature which use this notation, and it would just be a form of psychological warfare if I taught you a different notation, because then you wouldn't be able to read the papers anymore. Similarly, we have that. This is the whole reason we break up the field in this way. We're breaking it up into its annihilation operator part and its creation operator part. Now, if there was no time ordering symbol up there, then we'd be pretty quickly able to evaluate that expression now. Just, we'd have to commute past daggers and A daggers and A's, and then we'd be able to evaluate that expectation value. All right, let's consider an expression involving this time ordering symbol and see what changes, if anything. This is an example, right? Let's see what this time ordering symbol does to an expression involving field operators. Well, we can make our lives easier by assuming that x naught is bigger than y naught. If we make that assumption, then we know how to write out this expression here. Right, this is not the, I've made an assumption here, this is not the most general expression you're going to encounter, but just suppose that x naught is bigger than y naught. Then we know what to do, right? We just, that equals that. Okay, it's just how the time ordering symbol works. And we're going to write that out now in terms of the phi pluses and minuses. Right, so it's going to be 4 terms, somewhat tedious. Let's get started. X, y, plus, minus, minus, plus, and then you can get real good at this by the end of this course. All right, that's what it equals. Let's take a look at this expression, and then we're going to put it into a different order. So remember, we have this neat fact, right, that phi plus, when phi plus touches a vacuum, it gives you 0. So a term like this, if I put the vacuum on either side of a term like this, that will be 0. And if I put the vacuum on a term like this, it's going to be 0. If I put the vacuum on a term like this, well, I don't know what that's going to be. But if I put the vacuum, yeah, that's as far as we can go. So having phi pluses to the right is kind of a useful thing to have, and phi minuses to the left, that's also pretty useful, because that will destroy vacuums that come on that way. So we're going to try to put all the phi pluses to the right. So, well, there's only one place where the phi plus isn't in the correct position, so to speak. Right? It's this guy here. So we're going to put phi plus in the correct position. And you can do that just by using the commutator, right? So So I've added 0. But I've added 0 in a way to put this phi plus in the right place. So you can quickly check that that guy cancels with this guy to give you the piece in the yellow circle. But it turns out we know what this thing is. We've already calculated this object. It's this thing called dx minus y. And it's proportional to the identity, this commutator here, which you can check just by looking at phi plus x and phi minus x up there. If you look at that expression there, you see that inside these integrals there's a's and there's a daggers. And we already know what the commutator of a and a dagger is. It's something proportional to the identity. It's either 0 or delta function. So we actually know what this thing is, and it's quite a simple thing, right? There's an identity there. If you do that, if you do this reordering here, then it's easy to compute our very first time-ordered expectation value. So this term is 0, this term is 0, this term is 0, this term is dx minus y, and that term is, in fact, any guesses? What's this term equal to? It's also 0. That's right. Fantastic. This is all, of course, in the case that x naught is bigger than y naught. But the time ordering symbol, you know, if x naught was less than y naught, what would have happened then? Just to go back to this expression here, suppose that x naught was less than y naught. Well, we'd have to exchange x and y there. The time ordering operator will put the y to the left. The time ordering operator will put the y to the left. The time ordering operator will put the y to the left. In fact, most of those terms will still be 0. Just because there's a y or an x, we'll still get 0 for the same reason. In fact, the only thing that changes is this thing here. When you do this ordering operation, you get instead dy minus x. So I made a mistake. Just check. Yeah, I do believe that's correct. But we had a name for an object that did this kind of thing. So we actually encountered this one time before. And the reason we encountered it before is I knew it was coming up later in the course, not because not because it was a natural object at the time. Okay, this one I'm sure about. Good. So that's a function, right? Some function, you can compute it. You get a number when you put x minus y in there. And we've discovered that the expectation value of this time order product of just two field operators is given by this function. That's why we introduced it so many lectures ago, because it was going to come up when we did perturbation theory. Which is fine, just when you have two operators. But of course, we don't just have two operators, we have like an arbitrarily large number of operators that we have to deal with in these expressions. And that's what we're going to focus on now. So when you see a result like this, it's very tempting to hope that it might work in some sense for more operators. And we get lucky, it very much does work. But why it works so well won't be really apparent until you learn about path integrals. So when you learn about path integrals, there's somewhat mysterious manipulations here with time ordering and so on become like one-line proofs. And these objects that appear, especially these green functions, you see exactly why they appear. And it's all thanks to the fact that you know how to do a Gaussian integral. So that's the beauty of the Feynman path integral. We're not going to cover that in this course, but it's just worth mentioning that that's a great mnemonic for how to remember these expressions once you've learned about it. Good. Before we do that, though, I just want a tiny bit more notation before I give you the statement of the more general result that we need. So we're going to give several notations for exactly the same thing, because it's convenient when writing these things out to have different notations. So we're going to use another notation for this Feynman propagator called the contraction notation. Whenever you see an expression like this, two field operators with a line above it, that's also going to be understood to mean that. And this notation extends to situations where there's operators in between these operators. So whenever you see an expression like that, with a line joining these two guys, that means pull them out and replace them with the Feynman propagator. It's called contraction. We're not done yet with the notation. we're going to introduce another ordering operation called normal ordering. And I'm going to define this by example rather than give you the actual full example, full definition. Normal ordering. It's far quicker to define this through one or two examples than it is to really tediously write out all the rigorous steps you need to give a proper definition. So, example 1. Example 1, normal ordering. It puts everything with a dagger to the left and everything without a dagger to the right. So that's going to be A, Q, dagger, A, P, A, R. The reason this notation is such a nightmare to define normal ordering is because we need a symbol for there being a dagger there or not there. So that's not very nice. And this is a dagger. Pluses don't make sense on annihilation and creation operators, so it's a dagger. I'll do another example. Well, it's just move all the daggers to the left and all the non-daggers to the right. And that's it. You're welcome to spend 20 minutes, half an hour defining that correctly, but I think you can see from these two examples and the text there what it's going to do in general. There's another notation for normal ordering that you'll often see. People put a colon on either side of an expression. It's another notation for exactly the same thing. I don't really like it because it's hard to see the colons, right? In a sea of operators, you tend to lose track of these things. But you must be aware that that notation is very much in common use. And you can see why I might have introduced this notation, because the manipulations that led to this result there involved putting things in normal order. And in fact, there's a neat way to summarize what I did in the case of two operators. So you can call this just an observation, but it will very quickly become a theorem. Yes, indeed. You can check that. Just go through the expression I had that I've now erased. No, it's still here. So if we compare the left-hand side and the right-hand sides here, so left-hand side is this left-hand side, so that's good. And so the right-hand side is this right-hand side down here, for example, equal to the normal ordered version of that plus this? Let's check. Well, one term we've got for free, right? This guy here. Yep, those two match up. What about these? Well, there's 4 of those terms. Here they are, 2, 3, 4. And indeed, they're all in normal order, right? You can check that all the pluses, which have the A daggers in them, A non-daggers in them, are to the right. And all the A daggers, which are in the minus terms, are to the left. In all of these 4 expressions there. So indeed, it matches up. Let's check a more complicated example. Now in my notes I used copy and paste to do this example because there's 16 terms that we're going to have to calculate. But on the blackboard I don't have a copy and paste function, at least not on these blackboards. So I'm going to have to write it all out and I hope I don't make a mistake. And I'm going to make you write out all 16 terms. In fact, there's more than 16. I'm going to make you write out all these terms for a very simple reason, and that is to convince you that it's a stupid thing to do to write out all 16 terms. And once you've done that, then you'll be much more receptive, I think, to a diagrammatic way of dealing with these expressions. All right, well, we can agree, I guess, that this is going to be phi 1, right, phi 2, and so on. I'll put that notation up here. I think we can agree on that notation at least to make it a little bit easier. So what happens if you do exactly what we did over here, but on this? Well, okay, step 1 is easy, right? We get a phi plus and a phi minus for this term. We get a phi plus and a phi minus for this term. We get a phi plus and a phi minus for this term and a phi plus and a phi minus for this term. That makes 16 terms. But it doesn't stop there. There's more than 16 terms. Because some of those terms you want to move around into the correct order. And every time you do so, you pay a commutator penalty. So there's 5 terms, right? So we started with 4, but we ended with 5. If you imagine that we're going to do all those steps on this, and we are going to do those steps, we're going to end up with more than 16 terms. Well, let's see how it works. And I'm even going to skip steps, right? This is going to be an exercise. All right. Normal ordering is what we want at the end. So if you normal order all these guys, then we've got kind of like the analog of these first 4 terms here. But this side is definitely not equal to this side. Right? We have all these commutators that we didn't put in yet. Now we've got to put in the commutators. And boy, there's a lot of them. There was a commutator coming from 1 and 2. I don't need my notes. I should be able to do this without them because I know the diagrams. So. All right, there's a commutator coming from 1 and 3. commutator between 1 and 4. Remember how to do these contractions up here. Aha, but wait, there's still more. There's the commutator between 1 and 3 and the commutator between 2 and 4. There's a commutator between 1 and 4 and 2 and 3. And there's one. Yeah, but there's still some more terms. Of course, I forgot some terms. There's 1, 2, 1, 3, 1, 4, but there's also 2, 3, and 3, 4. 2, 4, sorry. What? But there's also 3, 4. Mm-hmm. Two, 4. And then I think that's it. 1, 2, 3, 4, 9. Yep. Okay, you're very welcome, and I invite you to do so, to write out the missing steps. Yeah, I see that the enthusiasm is very low. We have a way of writing this right-hand side here that's much more compact, which I'm sure you'll enjoy. That's the more compact way of writing what I just wrote out. Another way of saying that is to say that the normal ordering, that the time ordered operator of phi 1 through to phi 4 is the same as the normal ordering of phi 1 through 4 plus all possible contractions. Do you see, if you pick any pair of field operators, they've been contracted somewhere in this list. And then you've also got remaining operators, which you also have to contract. And all possible contractions of contractions are in there as well. So that's how we define that expansion there. And there's a theorem, which you'll enjoy, that says that this pattern continues and you need never have to do this tediously term by term ever again. And the theorem is very simple to state. It says that the time ordering of n operators is equal to the normal ordering plus all contractions. And we even have time to prove it today, mostly. And the way we're going to prove it is, I hope not surprisingly, induction. I hope that's not a surprise to you. Actually, I think the path integral proof isn't by induction. Interesting. Okay, so it's true for n is 2. We've proved that already. So we got the base case. So we just have to worry about how to get from the statement, we'll call this Wn, the statement that this equals this. We need to go from the statement Wn minus 1 to the statement Wn. Does the statement of Wick's theorem for n minus 1 imply the statement for n? So we're going to assume, without loss of generality, that x naught 1 is bigger than, oops, wrong way around, naught to, let's assume that everything's in time order, just so that we can, otherwise it's a permutation in this argument here to put that in the correct expression. Now, therefore, we know what the left-hand side is. And we're going to use the inductive hypothesis right there. We're going to use the inductive hypothesis to put this, to replace this, which is in time order, via Wick's theorem into something involving normal orders and contractions. That's the statement Wn minus 1. That's where we're applying it. We're using the inductive hypothesis right there. There, we've used the inductive hypothesis, and we've written down an expression that is true, right? Because we assumed it to be true. The time-ordered, I can put that back in. The time-ordered product of phi 1 through to phi n is equal to phi 1, which is just phi 1 plus phi 1 minus, multiplied by the normal order of all that stuff, as long as it does not involve phi 1. That's the inductive hypothesis. We've used it. In the next line, things are looking promising because one of these terms is already in normal order, so that's already useful, right? The phi 1 minus term is in normal order still, so we can just put it straight into the n. there's a lot of terms going on now that we have to focus on separately. So I'm going to focus on one of the two terms that appears in here. The right-hand side consists of more than just that term. The right-hand side consists of this term, which is sort of already correct. This term, which is already correct. This term, which is not correct. And inside here, of course, there's the phi's up to n plus the all contractions thing, yeah? Dot, 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 dot. And that's a 2, not a 1. So I'm going to deal with the first term inside the brackets here and leave the second term alone for the moment. So this is not in normal order because you've got a phi plus on the left and that should be all the way over on the right. But we know what to do with that. We always know how to get from left to right. You just put in a commutator. So commutators always put things in the correct order, but you have to pay the price of the commutator. Now this expression here is in normal order, so we get to put it inside the bracket in its rightful place. All right? Because phi 1 plus is indeed to the right, it's exactly equal to the normal order of phi 1 plus being to the left over here. Because the normal ordering, all it does is it says, okay, I've got to pick that up and put it over here. So that's what it does. But we've got this expression here. And for this, we use this Leibniz property of the commutator. And this is a bit tedious. And that works because these commutators here are proportional to the identity. If they were not proportional to the identity, what I just wrote here would be wrong. That needs you to think about it for a second. All right, we have another notation for that, which we should exploit if we can. And so on. We have n minus 1 contractions here. Yeah, n minus 1 contractions. Okay, that's fully processed that term here. The last bit of the proof will be some words, because there's only one term missing from having done the whole argument, and that is this bit here, the all contractions not involving phi 1 part. Once you've done this, then you should, and once you've convinced yourself that this is correct, then the last bit of the proof, which needs to deal with this part here, so the last bit, I hope the fog should lift, and then you should see how it works. So what's this going to consist of? This is just going to consist of products of field operators multiplied by some number of these Feynman propagators. And there's nothing stopping us using exactly the same argument we did here on every single term appearing in here. So we do that, right? You get a commutator, blah, 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 plus, of course, we put the n, blah, blah, blah. Okay, that's exactly the same trick we used up here. This is okay, right? This is a good term. This term here, we're going to do exactly what we did up here. And it generates all contractions, the normal order of all contractions with phi 1, or just all contractions. Because you pick up an extra contraction of phi 1 plus, with phi 1 plus, sorry. You pick up all these contractions with phi 1 plus that were missing before. And like that, we're done. That was it. That's all the terms accounted for. And we're going to put this observation to work to calculate time, the expectation values of time orderings of operators in the interaction picture. Now, the good news is that this is a theorem and it does simplify our job. The bad news is that it's still exponentially complex to deal with these expressions when n gets large. There's just no way around the fact that if you have an expression with n field operators in it, there's actually still an exponential number of terms on the right-hand side in n. So we're never going to be able to do like fantastic computational feats by employing this theorem, but it will organize things very nicely for us. Later on we'll see that we can simplify things, but I don't think I need that. Later on we'll see that we can simplify things by observing structures about these Taylor series, but for now this is as far as we're going to get. I'm just going to show you this result in practice and then draw a picture, and then we'll be on our way to our Feynman diagrams. And that will be the end of the lecture for today. So Let's do an example, because I kept this deliberately on the board here. Let's put that theorem now to good use. We want to calculate the expectation value of phi 1, phi 2, phi 3, and phi 4. How do we do that? Well, we know that we can employ Wick's theorem to put it into normal order. But the expectation value of the normal order of phi 1, 2, 3, 4 is 0. Right? I'll write that out, yeah? So this is 0, normal order, phi 1, phi 2, phi 3, phi 4, plus dot, 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 dot. If you normal order these operators, that means you put all the annihilators in front of the creators, and the annihilators annihilate the vacuum. So it's got to be 0. Let's apply that argument once more. If I apply the argument to this guy here, so this phi 1 and phi 2 is a function. It's the Feynman propagator. But there's still two field operators left over, and the normal ordering operator puts the annihilators in here to the right and the creators to the left. You get 0. In fact, you get 0 as long as there's any field operators in this expression at all. So let's go through the terms. Here you get 0 because there's some field operators left over. Here you get 0, there's some field operators left over. Here you get 0, there's at least one field operator left over. You get 0, you get not 0. Because there's no field operators left over. It's just proportional to the identity. Here you get not 0, here you get not 0, but here you get 0, there's some field operators that haven't been contracted. 0 and 0. There's only 3 terms left over at the end. And those 3 terms are delta f x1 minus x2, delta f x3 minus x4, plus delta f x1 minus x3, delta f x2 minus x4, and delta f, I won't fit it there, plus delta f x1 minus x4, 3, delta f x2 minus x3. These are the 3 terms that are left over from deploying Wick's theorem on this sum of 9 terms here. And we draw a little picture to indicate, to remind ourselves what these terms are. And the picture is, whenever there's a Feynman propagator involving variables xj and xk, you draw a line between 2 dots named xj and xk. So I'll do these pictures here. There's 3 pictures. This is 1, 2, 3, 4. I'm not going to define anything today, but this picture, I hope, will be suggestive enough that when we come to the proper definition in the coming lectures, you won't be surprised by what I say. So here, x1 and x2 are joined by this function, and x3 and x4 are joined. So I draw a line between those 4 dots there. Here, x1 and 3 are joined, and 2 and 4 are joined. And here, 1 and 4 are joined, and 3 and 2 are joined. So we've just calculated our very first Feynman diagrams in reverse, because we came up with the value of the Feynman diagrams, which is this thing here, and then we drew some pictures to represent these terms. What's going to happen in the future is that we're going to do the opposite. We're going to write down some rules, a calculus for these diagrams. These diagrams will be simpler to manipulate than these horrible Taylor series. We will do as much manipulation as we can on the diagram level, and only at the very end, when we've done all those manipulations, we'll convert these pictures into expressions involving the Feynman propagator. The final answer after about 5, 6 lectures is going to be that every process will be the sum of integrals of products of Feynman propagators. That's it. It's the only things we'll encounter after we do many, many summations and many, many Taylor series and many, many contractions That's all that's left over, integrals of Feynman propagators. And I think on that note, I'll finish. Thank you very much.